Alright, let's start with the doubt sheets. Okay, first question is, given a Hessian, how do we decide in which part of the domain it is positive definite? Okay, like yes, the previous example where we had the example of the function where it was it looked like a upward opening bowl, but there was one point where we calculated the Hessian, it was not positive definite. I guess motivated by that is the question, how do we decide which part of the domain it is positive definite? There is no easy answer to it, that is the short answer. You have to either come up with some kind of analytical guarantee or a proof that it is positive definite, or at each point that you are solving the problem you have to numerically verify that it is positive definite. Okay, there is no real good solution to it, which is why second order methods are often not used when the number of dimensions becomes larger. Okay, so the question is let me write down the expression. This has caused some amount of confusion. So the question is that this P over here, is it any arbitrary direction or is it pk? Okay, so there is a little bit of confusion and I am partly to blame for it. So technically what I should write, what I should have written is this. What were we trying to do? We were trying to say I am at xk, I am going to xk plus 1, and the direction which I end up choosing, the best direction, I am calling pk. That is what we have, right, and we are going to walk some length along this direction. Now when I am standing here, all options are open to me, okay, including many descent directions, right. Now in trying to, in the Newton method, when I wanted to find out the best P, what did I say? I set this equal to 0, right, and that is how I did some further manipulation and came up with the Newton direction. What I should technically do is, I should say in the language of optimization, argmin P is the variable of optimization. Okay, so let's restart this discussion. The question is, here is what is the P over here? That was the question. I have the Newton direction calculation. So technically what I should write it is that to get the Newton direction I need to set this gradient expression to 0, right. That is the same as putting mod of that, or you can say norm of that, to 0, since it is a vector, right. This is going to achieve minima at 0 because it is a norm expression, and I want the argument that minimizes this. So what is the argument? The variable of optimization is P. P is the guy that is floating around, that is in my hand, all of these different directions over here. These are my possible different P's, and I am going to select the best P from it. That solution is going to be called pk, right. So I was being a little sloppy, this is the fully correct way of writing it. Pk is equal to the solution to this optimization problem. So you know, until the problem is solved, it is just P, it is not yet pk. The best of the P's is what is going to be called pk. Does that clarify it? For the student has not written the name. So then there was another question that we assumed that the Hessian is symmetric, that is because of the mixed partial derivatives, and there is a theorem which guarantees that mixed partial derivatives are symmetric, like d this, right, this is actually equal to this, you can change the order, right. So this does not come for free, there is a theorem which gives this to you. Do we need to check this? So this holds true under the assumption that these mixed partial derivatives are continuous, right. So do we need to check it? Yes. Yeah, okay. Alright. Why should there be an open neighborhood around xk when we do gradient descent at xk? So the whole point of having an open neighborhood is that you need to have some non-zero points where you can actually do a gradient descent, right? So that's why you need open neighborhood. Okay. When we solved this equation, just look back at the expression that you got for the Newton direction. Was it unique, or are there many possible P's that satisfy this? Look back at the derivation.
As long as Hessian is invertible.
Obviously, the Hessian has to be invertible for the expression of the Newton direction to make sense, right? So let's write down that Newton direction. So Pn was equal to negative of inverse Hessian times grad f. Is that right? I'm going to ignore the 1 by epsilon over here. The direction is this. Now there is no ambiguity over here. As long as this is invertible, that means the inverse of a matrix is unique, multiplied by grad f, this expression is unique. So there is no chance of there being several Newton directions. There is one Newton direction if it exists, right? So remember, the basic story of the line search method is I'm here, I want to go here, okay, I'm going to walk some distance over here and in the direction pk and a length alpha, okay. So xk plus 1 is obviously, I write it like this, okay. Now in a line search method, I'm going to say that pk is fixed, okay. Pk, of course, as we saw in when we spoke about descent directions, it is not unique. There are infinite descent directions. You could pick any one of them. It's a legitimate descent direction. Having fixed it, what does a line search method do? It gives you the how much to walk, right? The step length. This is to be decided. So that is what a line search method will do, is it will, once you fix the direction, it will tell you how much to walk. This step length is the slightly old fashioned name for it. People in machine learning have given it a much fancier name. They call it the learning rate. Idea is the same. Sounds a little cooler, that's all. Okay. Okay. Now if we take small values of alpha, right, then if we go in a descent direction, we can assume that f of k plus 1 is less than f of k, right? That's kind of the whole motivation over here. So if I consider this grad fk transpose times pk, what will be the sign of this expression?
Negative.
If it is a legitimate descent direction, this has to be less than 0. Okay, this is something to keep in mind. Okay. So to find out, see, remember alpha is a scalar quantity, right, and which is what I want to compute. So what will be convenient is for me to define a scalar function of alpha which captures the whole dynamics of it, right. So I'm going to define a new function. I'm going to call it phi of alpha. This phi of alpha is nothing but a rewriting of this guy. Okay. And should we restrict alpha in any way? Can alpha take positive values, negative values, or, right? We are going to say alpha should be greater than 0 because since pk is a descent direction. Okay. Now, without solving the problem, actually, let's think of the goal. What is our goal in terms of phi or phi prime of alpha? What is our goal? What alpha would be the best for us? What property should it, or what quality should it have? what is the desired quality of alpha? Shouldn't be too large or should not be too small. Okay, can we be a little more ambitious? Should be the least possible value.
Once we take alpha, it should go to the least possible.
The function should go to the least possible. Okay, so we should pick that alpha such that the function reaches the least possible value, right? In that direction. So he's right. Can we sharpen that and quantify that a little bit more? Correct. So the least possible value, what is the signature of a least possible value of a function? Its gradient. If the gradient of that function is 0, that means that is a signature for a stationary point. So I want to find that alpha such that the function value is as less as possible, which is the same as saying that gradient of that function is 0. Right? So what we actually desire is okay. This is what we want. So now let's go a little bit deeper now. So I'm going to plot alpha on the x-axis, and I need to start only at 0 because alpha should be greater than 0. Okay. Now let us say that my function looks something like this. Okay. Now already we know that this is a non-convex function. So this is a discussion that is more relevant when the function is a general function, need not be convex. Okay. But we are assuming continuity, differentiability, nice things so that we can do calculus on it. How many interesting alphas are in this graph? 3, right? Because there are 3 points at which the gradient is vanishing, right? So this is, for example, alpha 1, alpha 2 and alpha 3. Okay. Now in answering this question that there are 3 interesting alphas, all of you made a very, very strong assumption that it is very easy for me to draw this graph. And that is a question that in data science and big engineering applications is a big assumption, right? Normally what is it that you start with? Where does the problem start? At what value of alpha does the problem start? When you're given the problem, you're at xk. So that corresponds to alpha equal to 0, right? So we are starting at what does that correspond to on this graph? A single point. It tells me I am over here. Okay. Supposing I further give you alpha dash, I mean the value of the derivative at the starting point, then maybe I have phi of 0 and phi dash of 0. That means I know kind of this slope over here. That's all that is given to me. Now in many real life problems, computing phi of alpha and phi dash of alpha is expensive. Right. So for example, supposing you were designing an antenna and you were varying the dimensions of the antenna. Every time you change the dimension of the antenna, you want to check how good of an antenna is it. But to know how good of an antenna it is, you need to put it into a, let us say, electromagnetic simulation software, which let us say takes 4 hours to give you one dot on this graph, right? So it's very easy for me to draw this graph, but actually to produce this graph maybe 1 week's worth of effort. So I cannot take this graph for granted. What is the bottom line? That even though I can see there are 3 interesting alphas over here, there is no, I mean if I could have this graph, I don't need to do any line search. I can automatically say that alpha 3 is the best, it gets me to the global minima. I need not bother with alpha 1 which is a local minima, or get fooled by alpha 2 which is actually a local maxima, right? So because these are expensive, the conclusion is that getting the exact value of alpha is often not practical. Therefore, what do we have to settle for? An inexact value of alpha, right? So exact alpha not practical. So we choose an inexact alpha. Okay. This is also called inexact line search. Okay. So what we'll do is, now the moment we say inexact line search, sort of the possibility opens up for all sorts of heuristic ideas. You know, how do we choose alpha? That is basically the bottom line. And because we have said that pk is a descent direction, for example, if I start every algorithm with alpha equal to 10 to the minus 8, will it work? Or some very small value, pick your smallest value, favorite smallest value, will it work? Will it work? I am not asking is it fast or slow, will it work? It works. If I pick a very, very conservative number, it will work. At some point when I get close to grad f equal to 0, I will say, okay, very good, I solved the problem. Of course, that is not practical. So we need to come up with some guidelines by which we can pick this alpha, right? And since we are all late to the game, someone else has already discovered it and their name is behind it. So they are called the wolfe conditions. But they are so simple that, you know, if you were born, I don't know, 60 years ago, you could have discovered them one boring afternoon.